5.4 Inverses of matrices and matrix equations. Multiplying any matrix by its identity matrix results in the original matrix. For example, A times I sub n is equal to A, and I sub n times B is equal to B. It's just like multiplying a number by 1. 3 times 1 is 3. The identity matrix I sub n is the n by n matrix for which each main diagonal entry is a 1 and for which all other entries are 0. An identity matrix is always a square matrix. For number 1, multiply to prove the properties of the identity matrix. Multiplying the 2 by 2 square identity matrix by this 2 by 3, we should get this 2 by 3. But let's try it out. Remember to find inner products by multiplying row by column. This actually makes sense because 1 times 3 is 3 and 0 times negative 1 is 0. So yeah, we would still have 3 in the top left. 5 times 1 is 5 and then 2 will be multiplied by 0. 6 times 1 is 6 and 7 is multiplied by 0. Same for the bottom row. 0 times 3 is 0 plus 1 times negative 1. Then we have 0 times the first row and 1 times the second row. So 2. 0 times 6 plus 1 times 7. Let's try it with a 3 by 3 matrix. When you find those inner products, you have negative 1 times 1 and 0 times the rest of the first row. Then 1 times 7 and 0 times negative 1 and 1/2. And then 1 times 1/2 and 0 times negative 1 and 7. As you continue to find these inner products, you'll see that you do have the same matrix that you began with. Inverse of a matrix. Let A be a square n by n matrix if there exists an n by n matrix A inverse with the property that A times A inverse is equal to A inverse times A, which is equal to its identity matrix. Then we say that A inverse is the inverse of A. Verify that B is the inverse of A. For A and B to be inverses, A times B needs to equal the identity matrix, and B times A needs to equal the identity matrix. So let's multiply A times B. Find the inner products. And you get the identity matrix, 1, 0, 0, 1. Now multiply B times A. This is also the 2 by 2 identity matrix 1, 0, 0, 1. Therefore, A and B are inverse matrices. Finding the inverse of a 2 by 2 matrix is actually pretty simple. Given the entries of matrix A are A, B, C, D, then the inverse of A is equal to 1 over AD minus BC times D negative B negative CA. If AD minus BC is 0, then A has no inverse. For number 3, find A inverse given A. How can you check your answer? First, let's establish A, B, C, and D. A is 4, B is 5, C is 2, D is 3. So filling out the formula for A inverse, we have 1 over 4 times 3 minus 5 times 2. In the matrix, we switch the positions of A and D, and we change the signs of B and C. Multiply 1/2 by 3, negative 5, negative 2, 4. And your inverse matrix is 3/2, negative 5/2, negative 1, 2. To check our answer, we know that any matrix times its inverse should equal the identity matrix. So let's multiply A times its inverse. Find the inverse of an n by n matrix. For 3 by 3 and larger square matrices, construct the following n by 2n matrix with A on the left and the identity matrix on the right. Then use elementary row operations on this new large matrix to change the left side into the identity matrix. The new matrix on the right will be your inverse. For number 4, find the inverse of A. A is a 3 by 3 matrix, so we will construct a 3 by 6 matrix with the entries of A on the left side and the identity matrix on the right side. Now it's time for us to transform the left side into the identity matrix, or basically to put the left side in reduced row echelon form. Every operation you perform on each row will be performed on the entire row, all 6 entries instead of just 3 this time. To begin, we already have a leading 1 as our first row, first column, so use that to eliminate the 2 and negative 3 below it. Conveniently, that also turned this basically into triangular form. Now I need a leading 1 in the third row, third column. So I'll multiply this row by 1/3. It's very difficult to completely avoid fractions when finding an inverse of a 3 by 3 or larger matrix. Continue transforming the left side into the identity matrix. We'll use the leading 1 in the second row, second column to eliminate the negative 2 above it. Wow, that also eliminated negative 4 in the third row. Very convenient. Now all we need to do is eliminate this 2 by using the leading 1 in the third row, third column. Now that the left side of your 3 by 6 matrix is the identity matrix, the right side is your inverse matrix. We can check by multiplying A by its inverse, and that should be the identity matrix. For this, I'm going to do the inner products in my head. I multiply each pair of numbers and say them aloud, and then add them up. Negative 3, 8, negative 4. That would be 1. First row, second column. 2, negative 2, 0. First row, third column. 0, 4/3, negative 4/3. Second row, first column. Negative 6, positive 12, negative 6. Second row, second column. 4, negative 3, 0. Second row, third column. 0, positive 2, negative 2. Third row, first column. 9, negative 24, positive 15. Negative 6, positive 6, 0. And 0, negative 4, positive 5. Yay, that's the identity matrix! So our inverse of A is correct. Number 5, find the inverse of the matrix below. This is a 3 by 3 matrix, so let's finish by constructing a 3 by 6 matrix and put the identity matrix on the right side. Uh-oh, our first row, first column is not a 1, but the first column for the other 2 rows is 1. So I'll just switch row 1 and row 2. Now use the leading 1 in row 1 to eliminate the 2 and 1 below it. At this point in time, I would usually multiply everything in the second row by negative 1/7. And like I said, fractions are usually unavoidable when finding the inverse of a matrix. But because I see there's a negative 1 below it, I'm actually just going to switch rows 2 and 3, and then multiply the new row 2 by negative 1. Honestly, I may have added more steps for myself. So if you wanted to just multiply the second row by -1/7 to get that leading one, you could absolutely do that. And then continue working with fractions for the rest of the steps, which, like I said, honestly may be unavoidable. So now let's multiply row 2 by 7 and add it to row 3 to eliminate the -7 in row 3. Uh-oh, now I have all zeros in the third row on the left side. How do I get a 1 back? Any operations that you may do in order to try to get a 1 in the third row, third column, will turn the zeros in the third row back into other constants, resulting in an endless cycle of trying to turn one of the zeros into a 1 and keep the other zeros as zeros, which is impossible. We cannot rewrite this matrix as an identity matrix using row operations. Therefore, this matrix has no inverse. Solve the matrix equation below for x. Matrix A is known as the coefficient matrix. Instead of having the coefficient of A, I want x to have the coefficient of 1. So what can I multiply by A in order to get 1? Or the equivalent of 1 when it comes to a matrix, which is the identity matrix. Well, I'll just multiply both sides by A inverse. A inverse times A is the identity matrix, which is equal to 1 in this matrix equation, and that means that x is equal to A inverse times B. For number 6, write the system as a matrix equation and then solve. In 5.3, we rewrote a matrix equation as a linear system. So begin by rewriting this linear system as a matrix equation. Use the coefficients of x and y to create a 2x2 matrix. Multiply that by a 2x1 matrix with the variables x and y, and that will equal your results of each row, 15 and 36. This is like the form above. You have the coefficient matrix A times some unknown matrix values x equal to B. The solution to that matrix equation is x equals A inverse times B. So let's find A inverse. Fortunately, A is a 2x2 matrix, so we can use the formula to find its inverse. 1 over AD minus BC times the matrix, switch A and D, and then change the signs for B and C. This makes A inverse -2, 5/3, -1, 2/3. So the unknown matrix X, which in our case is XY, is equal to A inverse, this 2x2 matrix, times B. Now find the product of A inverse and B. Your resulting matrix will have dimensions 2 by 1. The first entry is 30 and the second is 9. This means that x is equal to 30 and y is equal to 9. Wow, that was so cool. You just throw the matrix in the blender and then multiply it by another matrix and then poof, you have x and y.